that. So the definition derivative basically looks like this. The limit of, as x approaches 0, of f of x plus h minus f of x all divided by x plus h minus x. You can see that's just slope. If we cover up if we erase actually the limit, it's just slope. Just y minus y and x minus x. Of course, but when we put the limit back in, limit as h approaches 0, now it's the instantaneous slope, because we're letting the 2 points get closer and closer together, and asking what is that quotient headed towards as h gets closer and closer to 0, or as the points get closer and closer together. That means the secant line that we're finding the slope of is getting closer and closer to the tangent line, which tangent line represents the slope, instantaneous slope at that point. So if I wanted to apply this to f of x equals x squared, did this in class, but I'm going to do it again here. So that would be the limit as h approaches 0 of x plus h squared minus x squared all over, and of course x plus h minus x is just h. And if we do some algebra, notice I'm rewriting the limit. If we do some algebra, we get x squared plus 2xh plus h squared minus x squared all over h. And when we multiply that out, we notice the x squared and the negative x squared cancel each other out. So we're left with the limit of 2xh plus h squared all over h as h approaches 0. And notice there's h is a factor at the top, so we can cancel that out. And that leaves us with the limit as h approaches 0 of 2x plus h. Now we can let h approach 0. As h gets closer and closer to 0, 2x plus h gets closer and closer to 2x. And just to do another one that's similar to what we just did, if we do, I think we talked about in class 1/3 x squared. So that would be the limit as h approaches 0 of 1/3 times x plus h squared minus 1/3 x squared all over h, because that's again x plus h minus x. And that would be the limit as h approaches 0 of 1/3 x squared plus 2/3 xh plus 1/3 h squared minus 1/3 x squared all over h. The x squareds, the 1/3 x squared, of course, cancel each other out because one's positive and the other's negative. And we're left with the limit. Oops, I made that too big, didn't I? Too thick. The limit as h approaches 0 of 2/3 xh plus 1/3 h squared over h. We can factor out h from the top. We're left with the limit and cancel it with h in the bottom, and we're left with 2/3 x plus 1/3 h. And when we let h approach 0, this approaches 2/3 x. And the hypothesis in class that it would produce 1/3 what the x squared did. So there are some good examples of some different functions using the factor and cancel method. But let's do one using the rationalized method. So here we got f of x equals square root of x, and we want to find the derivative. We want to find a formula for the derivative of this function at any point on the function, on the graph, I mean. So again, this would be the limit as h approaches 0 of the square root of x plus h minus the square root of x all over x plus h minus x, which is just h. Plug in 0 doesn't work because we got divided by 0, so we're going to have to do something to this to make it look different. And this, because of the square roots, I think of rationalizing the denominator or the numerator. So we're going to have the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h, and I'm going to multiply top and bottom by the square root of x plus h plus the square root of x. Square root of x plus h plus the square root of x. And when I do that, I get the limit as h approaches 0, and on the bottom I'm going to have an h here times the square root of x plus h plus the square root of x. And on top, this times this is going to give me just x plus h, and the middle term and the outside terms are going to cancel each other out, and then in the end there I'll just have a minus x. And notice something wonderful happens. The x minus x is 0, so now I'm left with the limit of h on top and h on the bottom times square root of x plus h plus the square root of x, and h approaches 0. The h's can cancel out, so now we have the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now we're ready to let h approach 0. When h approaches 0, this gets closer and closer to 1 over 2 times the square root of x. All right. So hopefully this is helping out, making things clearer. I'm going to do one more example, a basic one with f of x equals 1 over x. So we do the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. Remember that comes from x plus h minus x. And in this case, we have fractions, and it's not very nice to play with fractions. Or fractions don't play very nicely together when they're mixed in with each other. So we want to try to, this is a complex fraction, actually we want to try to get rid of that. So one thing we can do here is multiply top and bottom by the common denominator. So you can multiply the top by x times x plus h, and the bottom by x times x plus h. If we do that, we end up with the limit as h approaches 0 of, now when I multiply this times that, I'm left with just an x. When I multiply this times that, I'm left with just a minus x plus h. And then on the bottom, I'm going to have h times x plus h. And as usual, something wonderful happens. X minus x, of course, is 0, so I'm left with just a minus h up on top. I still have the hx outside here times x plus h. And of course, the h's cancel out. That leaves me with the limit as h approaches 0 of -1. That's important to notice there's a -1 up there. And on the bottom, I have x times x plus h. But of course, as h gets close to 0, this bottom just becomes x squared, doesn't it? So I have -1 over x squared. So what is -1 over x squared? -1 over x squared is a formula that you can use to find the slope, the instantaneous slope, at any point on the graph of 1 over x.